All right, hello everyone. Welcome to your lecture. Today we're going to be going over binary numbers. Binary is the way computers represent numbers. So let's talk about that. How does a computer represent numbers? Well, computers speak a language consisting of two signals. The signal is either going to be on, which is represented by 5 volts, or off, which is usually represented by 0 volts of electricity. So computers use binary because they can quickly detect a voltage signal on an input. And then computers understand instructions which are written in binary. A cool example of adding two variables together. In Python, we've seen it as a equals a plus b. This gets compiled down to assembly, which looks like this instruction. We don't have to worry too much about assembly instruction, but the assembly instruction gets compiled down to binary. And the add instruction, add a and b together and store it back in a, actually looks like this string of numbers down here in binary. This might not be the exact representation for Python, but this is an add instruction that a computer could recognize. So you know that saying that says computers are made up of ones and zeros? Well, it's really true. And it's binary. So the question that comes is, why do computers use base 2, and then why do humans use base 10? And we're going to look more into what base is, but in base 10, we have 10 digits that we can work with. And the simple reason is that we have 10 fingers. If we had 2 fingers, we'd probably use base 2. So an example of this is in base 10, 11 is represented as such. We have 2 ones back to back. In base 2, 11 is represented like this, 1 0 1 1. We're going to look at how we got that in a few seconds here. So we're going to start out with how to read binary digits. This slide we have a comparison between base 2 and base 10. It looks like a lot of information, but we're going to start with base 10 down here. Essentially, each digit's place holds a specific value. The first digit is a value of 1, the second digit is the tens place, the hundredths place, and the thousandth place. It's very similar for binary. Each digit holds a amount of value. So the first digit spot holds value of 1, just like base 10, but it differs here. Our second digit place holds a value of 2, and then we multiply by 2 each time. We have 4, 8, and if we continue, we'd have 16, 32, 64. You'll see what I mean as we move on here. So let's see how numbers are represented in binary using this exponent value table. And we are going to come back to this slide once we've seen some examples for it to make sense. So here's the binary value of 1. We have 1 in this first digit spot, which has a value of 1. It's kind of straightforward here. Now when we move to a binary value of 2, we have this value, this digit, which is represented by 2 value, and this digit, which is represented by 1, as 0. So you may be able to guess for binary digit number 3 here. And it might be helpful if I can draw on this. So we have a value of 1, a value of 2, a value of 4, and a value of 8. So we can see how we got 3 here. We move to binary representation of the number 4. And so for 5, we'd have the 4 place and the 1 place. And then for 6, we'll have the 4 place and the 2's place. We'll keep going with 7. On 8, we clear everything. And we have the 8th digit, or the 8th value. and so on and so forth. So you're just counting in a different way. I'd almost argue it's very similar to counting in base 10, but we just have less digits to work with. Now that we've seen some examples, I hope this slide makes a little bit more sense of how each position holds a specific value. And so that brings me to what is the exponent up here. One of the ways to calculate what the value is going to be in a particular position is to take the base, which is going to be 2 in this case, and raise it to the power of the current position. So we're in current position 0 here, 1 here, 2 here, and 3 here. So to get this value, and this is a generic method, so if we have 32 positions, we'd be able to figure out what the value of the 32nd location is. We could just take the base and raise it to the power of the position. So unfortunately, I have to show the ugly form of how to figure out what the base 10 representation of a number is given any base. And so I'm probably going to draw this out, but just quickly here, if we have the binary number 1011 here, so we have 1011, a way to figure out what that number is in base 10 is to take the digit here and multiply it by the base to the power of its position. So we're in position 0 here, so we're going to take 1 times 2 to the 0. So 1 times 2 to the 0, 2 to the 0 is 1, 1 times 1 is 1, plus 1 times 2 to the 1 here. So 2 to the 1 is going to be 2, 1 times 2, we have 2. 0 times 2 to the 2, well, anything times 0 is going to be 0. And then 1 times 2 to the 3, 2 to the 3 is indeed 8, so 1 times 8 is 8. And so we have 1 plus 2 plus 0 plus 8 is indeed 11. And you can kind of see here that if this was a 1, this would be 4. And so this kind of matches what we just saw with the previous slides. And just to show you this works for any base, this works for base 10 as well. We have the same number 11, we have the 2 1s here, and if we take 10 to the 0 is 1, so 1 times 1 is 1, 10 to the 1 is 10, 1 times 10 is 10, so we have 10 plus 1. This is a way to figure out the base 10 representation given any base of numbers. We have base 2 all the way through 10, all the way to 16. This method will work. Alright, so we've talked a lot about binary numbers. Let's see how this relates to Python here. So any number in Python that is an integer, not a floating point, is going to be 32 bits. And each digit in binary is called a bit. So this 1 here is a bit, this 1 is a bit, and so on and so forth. Some other important names I should let you know about. The digit all the way to the right is called the least significant bit. And the digit on the left is going to be the most significant bit. And the reason they're called that is the value of this position is the largest and the value of this position is the smallest. So any number in Python can be represented by its binary equivalent. So this again is the number 11 that we've seen before, and so 11 in binary, as we can see, is represented by 1011. So let's go ahead and pull up Python. This is the Python basic executable for Windows. We can kind of just type commands in here. So we can say print hello, and it works just great. I'm just going to print the binary representation of the decimal number 11. And so we can see here we get the 1011, but we're missing all these other positions. These positions are there, but the fact that they're all 0, Python's just saying, hey, you don't need to know about that. We're going to kind of not show you. So we learned that we can figure out the value of a position by taking the base and raising it to the power of the position. So we have position 31. If we wanted to find the value of this position here, we'd just raise base 2 to that position. So let's figure out the binary representation of the largest value here. So we can see here, now we have the other digits that we were missing before because they are important now that we have a 1 to the left. So one cool thing we could do here is print out the binary representation of the first 15 digits or 16 digits, similar to what we saw in the slides. So in this Python application, we can actually run loops as well. For I in range 0 to 16, print the binary representation of I. And so we can see here that we get the exact same binary representation that we saw in the slides here. Pretty cool that we can go ahead and translate between binary and decimal by just using the bin command. So another cool thing we can do is print out the value of each position. So we could say for I in range is 0 to 32, print the decimal value of 2 to the current position. And so this will give you all the values of each of the 32 positions here. And so if I get this set up here, we see that the first position is value 1, value 1, value 2, value 4, value 8, and it multiplies by 2 each time here. So this does get to be a pretty big number here at the bottom. And you guys have maybe seen these numbers before. In some video games, this number is considered the maximum integer value. Like if you ever had the maximum amount of cash in a game, it might be this number here. And that's because the game is using an integer value to store the currency amount. Just a cool fact, a lot of games nowadays are using 64 bits instead of 32 bits, and that number is much bigger. Moving back into math, we're going to take a decimal number and we're going to convert it to base 2. It's not as hard as you'd think. A computer is very good at this type of process. Anything that is very methodical, step by step, a computer is very good at solving it. Us humans, we kind of just have to go through the motions to solve something like this. So let me show you an example. Let's say we had the number 90. And that is going to be in base 10 here. And we want to convert that to base 2. So the way we're going to do this is simply divide our base 10 number by 2, and we're going to get the value and the remainder. And we're kind of going to keep track of these two pieces of information, and we're going to use them to rebuild the binary number, to build the binary number. So we first have the number 90. and we're going to divide it by 2, and the result will be 45, and it has a remainder of 0. 90 divided by 90 divided by 2 is very clean. So now we're going to have 45 divided by 2, and we're going to get a result of 22 with a remainder of 1. So we're going to, every time we're going to take the value that we get from the division, and we're going to plug it in and use that to divide. So you can see how this is very methodical and very almost kind of straightforward. So we're going to take 22 and divide that by 2. We're going to get 11 with a remainder of 0. Then we're going to take 11, divide that by 2. We're going to get 5 with a remainder of 1. We're going to take 5 divided by 2. We're going to get 2 with a remainder of 1. We're going to get 2 and divide that by 2. We're going to get 1 with a remainder of 0. And we're going to take 1, divide that by 2. We're going to get 0 with a remainder of 1. So we're going to stop until we have a 0 here at the end. I'm sorry, we're going to continue until we get a 0 here at the end. And so essentially what we've done is we've built our binary number, but you have to be careful because the binary number is built from the bottom up. So we're going to have 1, 0, 1, 1, 0, 1, 0. Should be the binary or base 2 representation of the number 90. So let's go ahead and see if this is true. I'm kind of just going to pull up Python. And I'm going to print the binary representation of 90. And we're going to see if we got this right here. So we got 1, 0, 1, 1, 0, 1, 0. So it checks out. So this is going to be your method for converting from base 10 to base 2. You simply just divide by 2 every time. Take the value that you got from the division and divide that by 2. You keep dividing till you get 0. And then you take the remainders in reverse order and you have your binary number. So you know what's coming next. We got to go from base 2 back to base 10. And this is where that ugly math slide is going to come in handy. You can kind of play a game where, let's say you do have the number here, 1, 0, 1, 1, 0, 1, 0. So you can play the value game. Like for smaller binary numbers, I just want to share this with you. We know the values are going to be 1, 2, 4, 8, 16, 32, and 64. So if you're in a pinch and you just want to quickly figure out the decimal representation of a binary number, you can just add up the 64 plus the 16 plus the 8 and the 2, and we're going to come to the same result using the longer mathematical method, but I just wanted to share this with you. You can quickly figure out the value here. So given this binary number, we know its position. So we have position 0, 1, 2, 3, 4, 5, and 6. So the formula that we learned before is we take, I'm actually going to pull it up here. we take the number times the base raised to the current position. So we'll have here the number. We're going to start all the way on the left. You could start all the way on the right. It's up to your preference here. Sometimes if you start on the left, you're going to run out of space when you get to the numbers on the right. So sometimes you want to start on the right. It's really up to how you like to do your math. So you take the number and you multiply it by the base to the power of the current position. And we're just gonna kind of keep performing that same action. Nope. Messed up there. Alright, and then we kind of just do the math to solve this out here. We're going to have 0, 2, 0, 8, 16, 0, and 64. So we add up 64 and 60, 64 and 16 to get 80, and then 8 and 2, which is 10, that will be 90. So we successfully converted from 90 to the base 2 representation, and then we went in the other direction and converted the base 2 representation to the binary representation or base 10 representation of 90 here. So it's a very methodical process. The fact that it is methodical, I think we should code it up. We should code these two functions up, convert to base 2 and convert back to base 10. Alright, so the first function we want to write is convert to base 2, and we're going to take in a binary number here. And the process that we saw before was that we keep dividing until we get a value that is 0 or less than 0. So while value is greater than 0, we're going to perform these actions, and we're going to get the value by saying the new value is value divided by 2. And I guess we don't need int here. This value is already an integer. And the remainder is going to be value mod 2. So mod will return the remainder for us if there is one. And then we need a way to store the remainder. And the reason is that we're going to print out the remainders in reverse order. So we're going to have like a remainder list, and we should seed the value with the binary number. So back here in our loop, we're going to append to the back of the list the remainder. And then once that is finished, we're just going to print out the remainder list here. All right. So we're going to run this function here. This is called convert to base 2, and we're going to put in 90 again, and we will run this. I did have to, so what I did there was When we were dividing by 2, Python was converting it back to a floating point, and our output was messed up. So just to fix that, I made both the value and the remainder, I made sure it converted to an integer value. So we see here our result is 1011010. And if we go ahead and pull up what we had before, 1011010. So that checks out. That function looks great. Alright, so now that we are able to convert from a decimal number to a binary number, and I realized that I had written binary number in this function. I have changed it to decimal number. I apologize for that mistake. We're going to now convert to base 10, or we're going to take in a decimal number this time, and we want to print out the base 10 version of that number. And so we're going to play with the same numbers we've been using, which is going to be 90. So the process for this is that we want to take the current bit and multiply it times 2 to the power of the current position. So we're going to want to keep track of the current position. It's going to be the length of the decimal number minus 1. And the reason is if we have the number 1011010, the length is 1, 2, 3, 4, 5, 6, 7, but the positions will be 0, 1, 2, 3, 4, 5, 6. So this will be position 6 here. So we want to start here, position 6. And then we want to go through for every bit in binary number. We want to keep track of the result, so we'll have a result variable, and we'll say result is now the bit times 2 to the power of the current position. And then we're going to want to decrement the current position. So current position equals current position minus 1. And then, oh man, I went backwards this time. This should be binary number. I don't know why I got those two confused. We're going to want to convert a binary number to base 10. Yeah. Okay. And then at the end here, we're just going to print out the result. So we can do convert to base 10 with the binary number of 90 here. And let's see how this works. Oh, my apologies. Let's use a string. It didn't like that the B is in there. So 10111010. So we indeed get 90 as the result. So here, and let's add some feedback here. Print converting to base 10, and then the result is and yeah, so we converted 1011010 to base 10, and the result is 90. Awesome. Alright, so that will conclude today's lectures on binary numbers. I know it's a lot to take in. Definitely practice the conversion between a base 10 to base 2, and then back from base 2 to base 10. Also, I want to add that coding up those two functions, even though they're built into Python, it'll be a good practice to really get the idea down once you've been able to perfect it on paper. All right, well, thank you for spending a little bit of your time with me today. I hope you have a great day.